So when we talk energy resources, we'll start with a couple of points before we move forward. We'll need to agree on some basics, and hopefully we will all agree on them before we go forward. The amount of energy in the universe is fixed. We need to agree on that. So energy is never created, not yet. If you want to come up with a new way to create energy, I think you will get a lot of money. But until now, it's not. It's just being transformed from a type to another type to another type, and that brings us to the second law of thermodynamics, which is, in a way, will state that what will happen when we transfer energy from a type to another one? There will be always some sort of losses. So the transformation can only reduce the amount of energy available. Now, just probably before we move forward from this, because the second law of thermodynamics also talks about entropy and how the entropy is always increasing, but then energy is reducing. So we'll need to keep in mind here, the energy which is reducing is the useful energy, the energy which we can keep it transformed to get something useful. Okay? 100% efficiency is impossible, and in other words, it's impossible to convert heat completely into work in a cyclic process. You cannot do that forever. So keeping all these points in mind, we can move forward and talk about the resources. We'll get to know what type of resources we have access to, and we'll probably provide a bit of a brief introduction to each one of them as we go. So forms of energy, we have looked into this last week, and these are sort of forms which you expect and we are currently using and changing between one another. This was not covered last week, magnetic energy. Magnetic energy is, in today's magnets, is really a storage. So you build a magnet, you store that energy in it, and then you can use it. What's important to mention here, of course, not about the scale which we are going to talk about in foundation of energy, because we talk world and generation plants. But if you look online, so many times this is being referred as a free energy. You see lots of people talking about some magnetic field devices and they call them free energy. There is no such thing as free energy. There might be refreshments for free tonight, but energy, forget about it. So always there is a transformation and always there is a storage. That brings us to trying to identify the types of resources available. And that brings us to two types, finite and renewable. So can you give some examples on finite? Fossil fuels, yeah. It is a good example of finite. How about renewable resources? So if we just try to look into these two, how they really differ. I know this probably already make you think about quantity, and this is finite in quantity and this is renewable. But if we want to put this in a schematic diagram, we'll probably show you, then we'll discuss it easier. A finite energy, if we want to put it in a schematic diagram, will look something like that. So we do have a source. And that source, if you don't touch it, it will stay there. Now this doesn't apply on nuclear fuels because there is natural decay. But if we took other fossil fuels, for example, if you leave them there, they will stay, and they have been there for thousands and millions of years. What we need to do, we'll need to come up with a device, which we have managed to come up with many over the last 200 years, and then we start using and supplying it to the environment, provided the switch is closed here, which means we are accessing that fuel resources and start using them. So this is finite energy. there is always limit for what's there in that storage. Based on the current knowledge, there is a specific size of this store, which seems to be increasing in a good way with the oil, with gas, and so on, with the introduction of new technologies. If I ask you to come up with some similar schematic diagram for renewables, how do you imagine that will be?
Closed cycle.
Closed cycle. So it starts by the environment, moved, and goes back to the environment. The only difference there, it's always connected. You can't really switch it on and off. If the wind is blowing, the wind is blowing. The sun is shining, the sun is shining. So this is going in a closed cycle, always moving. What we need to do is basically introduce similar setup, and then we start to basically get that energy and use it as we move. Some of what we mentioned last week, this current of energy might be too powerful, like wind, for example. So we will have intentionally to open the switch and stop harvesting that energy. This is something you need to keep in mind. And then you will always have clearly the storage issues, because it will be going no matter if you use it or not. And then if you harvest or if you access that, you will need to immediately use it or basically store it. Putting some definitions for these two. Finite energy is going to basically be that energy which is obtained from stores of energy that remains more unless released by humans' activity. Renewable, on the other hand, it is obtained from naturally occurring currents. So these two things you need always to keep in mind when we talk finite or renewable. The stores for the finite and the occurring currents for the renewables. Now, if we want to give examples for each one of these, we got the fuels, which you mentioned in there, and some examples for renewables as well: sunlight, wind, and earth heat, geothermal. Do you think there is anything missing from this list? Biofuel or wood or biomass. Where do you think it belongs to? It is actually for both. It's something in the middle. It's something you can store and you can renew. But if you don't renew, you will basically, it will be finite and you will harvest it, burn it, and that's it. It's over.
Doctor,
Yes, please.
what about hydrogen?
Well, hydrogen, where is it coming from? Now, these sort of resources are already available for us. We are not making these. So the hydrogen which is there in the environment, which was basically released during the formation of Earth, it will fall in here. If it's something you are making it with renewable technology, then that is different. You are using water, or you are getting hydrogen, where you are getting hydrogen from. Now, if we just look into these and try to find the origin of all these resources, can you help me with that? Where do you think the origins came from? Sun, one of them, okay? And that is applied to sunlight and earth heat, which is the gradual cooling of Earth, basically, and
Wind.
come again?
Wind.
Wind. Well, if you think about wind, why we have wind in the first place? Gravitational force, yes, but not for wind. It's for maybe tides, for example.
Due to difference in pressure. Pressure due to the sun.
Sun. So we get back to sun. Yeah, which is basically, if you look to the globe and the atmosphere, solar activity is basically driving wind and rain. So evaporation due to heat, and it go rain on top of the mountain. We get hydros. Waves is due to the sun and the solar activity. Tides is only gravitational force and of course the Earth's heat.
What is the difference, waves and tides?
Waves is the waves on the sea which happens due to wind. Tides is the rotation of the moon around the globe which brings the level up or down. Okay, so this brings us to the origin of resources, and we got only 4. So energy released by the gradual cooling of Earth, and it's still being released at a good currents which we can use. Energy stored during the formation of Earth, an example of that is uranium, for example. Energy provided by gravitational forces and the solar activity. Now, if you look to this list, it doesn't really have what we have seen last week in all these figures with coal, gas, and oil, and everything is increasing. So where do you think that fit? The fossil fuels other than uranium. Where they came from? It's millions of years of vegetations, which was due to the solar activity. So basically, almost all what we have now, other than, of course, the gradual cooling of Earth and gravitational forces, lots of storage of solar energy on the planet. So oil, gas, all the coal, they are all basically from sun. It's a stored energy, which we are now accessing on daily basis. So let's try to divide these origins the same way, the 4, and we'll just give example to each one of them. And then you get long list goes with solar activity. Okay, so the ultimate resource is solar, and this all is being stored and we use it. Now let's try to put some numbers to all that. Resources available in terawatt. So the total required is about 15 terawatt. We get ocean tides about 2, hydroelectric about 3 terawatts, wind 4 terawatts, geothermal 12. So if you just add up all these together, other than of course the solar, they barely add up to what the planet needs. And this highlights how much solar energy we are getting and how much we can satisfy of the planet requirements if we can tap into that solar energy. So this will take us to a few slides on solar energy. Now the sun gives an energy flux of about, yes please.
So from photosynthesis we have 130 terawatt, right? How did you come up with this figure?
Well, this is estimated figures, so don't take them for granted. It's just to give you a feel of these numbers. Yeah. So we get solar global radiation. This is on top of the atmosphere. Before the solar radiation enters the atmosphere, we get about 1,360 watts per meter square. Some reference books might give it as 1,363. So this is going to be a sort of a golden number. We'll see how we'll convert that to each area solar radiation or expected solar radiation. Now we get that on top of atmosphere as long as the sun is shining. On the ground level, then all the cloud coverage, the angles, and all these come into place to estimate how much you get. So now if we want to know, this is per square meter by the way. So if we want to know how much we are getting to the surface, which area you think we should take? A disk area, pi r square, a sphere area, or half a sphere? Half a sphere. Anybody, let's start with A. Anybody says A? Disk? 1. Okay. B, anyone? A sphere? 0, which is good. Half a sphere, everybody else? Some people not raising the hand either way. Do you think there's another way to do it? Anyway, so the correct answer is A, and I will tell you why. Because if you look into the sun, which is like really far and really big, all this solar radiation looking from our small planet will look something like that. The sphere which you are guys talking about is here. But if you look to this energy, it's basically that disk area here. And then this will come and distribute to the half of the sphere. And the rest will basically go and hit other objects. So are we cool with the disk area? Because we'll a little bit confuse you next, and we'll tell you we'll use half the sphere for something else. But I promise the disk is the correct answer. Okay? So we are going to multiply that with the area. We need R. We have R. Again, is estimated R. It's not a perfect disk or a perfect sphere, but we'll live with that, and we will use this radius in this case. That will get us to this figure, a total energy of 174 petawatt. We have seen this last week as well. And we have seen also the 10,000 figure. So we get lots of energy from the sun, but we'll need to tap into it, use it, and it will satisfy a good amount of our energy requirements. Now, talking about radiation or light in general, we will see the spectrum of the solar radiation, and we know it has some other components other than the visible light. But most of it is actually in that visible light, plus a little bit of the UV and a little bit of the IR. So talking about light, physics 101, you will get the light either reflected, absorbed, or transmitted. You don't have any fourth component. So we will see how this will apply into our solar radiation. The energy balance looks like that. So you get about 100%, well, 100% in, 70% direct reach to Earth, plus a 7 scatter to Earth. We are interested in these. All your solar collectors are working on these, if they are at ground level. If you are building a solar collector up in the orbit, then you will get the 100%. And then you don't need to worry about any sort of coverage. You don't need to worry about cleaning as well, unless an old satellite hits your setup. Okay, so we got absorbed about here, and that is the ozone, and then there is the dust layer, the water, and so on. But what we are interested in is these two figures, really, 70 plus 7. In general, moving from 100% of 1,360, we assume about 1,000 watts per meter square reaching the surface on a good day. And of course, that will be subject to angles, and we will see that. So that will bring us to another term, which we call it air mass. How many of you familiar with air mass? No? Okay. So air mass basically is how much mass of air the light needs to go through to reach your solar collector, to hit the ground. Okay? So our air mass 0 here, there is no mass at all. And here where the figure 1360 come from. If you need to move in, then you need to basically calculate the air mass. Now, air mass 1 is very easy. is the shortest distance the light need to travel through.
Can you repeat the same answer?
Yes, I can. So air mass basically is a number which feed into your solar energy calculations. It refers to how much air mass the light need to pass through until it reaches your collector. So we measure that based on the atmosphere the light need to travel in. So outside the atmosphere, here at this point, this is AM0, air mass 0. There's no air. We haven't get into air yet. So we call it AM0. If you get to the shortest distance to hit your solar collector, then that is air mass 1. Okay? So 0 and 1, everybody clear on that? Then we can move to others. Now in every other place, there will be basically angle. You need to consider that angle in consideration, and probably we'll just use that as a bit more clear, theta in this case. So here air mass 0, here air mass 1, this is the minimum you can do, and everything else depends on theta. The air mass is going to equal 1 over cosine theta. So for example, if we take 48 degrees, that is going to give you air mass 1.5. Probably to be accurate, 48.6. And that will refer to all this belt here. Whatever located on this area or this line is going to be under that AM. Now if you just look to that 1 over cosine theta, you will immediately figure out there is a problem, which is when theta is 90. That doesn't work. So that is a sort of estimated value, which is accurate for most of the places which you are going to put solar panels. But keep in mind it doesn't work with theta equal 0. So this is something you need to keep really in mind. Your air mass is going to equal 1 over cosine theta. And if you know theta, basically if a question gives you a certain theta, you will just get cosine, invert that, you will get your air mass. Now we can also calculate the direct and the diffuse radiation, and we are going to use these two equations down there. Now, in exam, we normally provide data sheet. So before you ask, I will answer your question. Which formulas to remember, which formulas you expect to find? The answer is check the data sheet when you prepare for your exam. Then you will know what to expect. We normally have it on Vision before the exam. So you get yourself prepared. So if it's there, then that's it. At least you know how to use it. And if not, you'll need to remember it if you feel they are important to remember. Okay. Some more on solar radiation. This is a typical spectrum of solar radiation at AM0. So if I want to put AM, let's say 1.5 on top of that, do you think it's going to be lower or higher?
Low.
Lower, because there should be some losses. Do you think it's going to be identical to this, just running below it, or it will have different shape?
Different shape.
Why?
Because infrared, visible light and ultraviolet behave differently in the day.
Kind of. Any other thoughts? Ozone?
Because of the wavelengths. Some of the. It will get lower because of the wavelengths.
It get lower where? Because of the wavelength. Everywhere? So means it will look the same.
No, at the end of the day, because
At the end.
infrared-
Here.
Yeah, the infrared will be the longest wavelength, which has the least power.
Then infrared, that means then that side. Anyway, let's see it. So it looks something like that. Sort of expected lower in most of it, but then we got these areas. Now this area refers that a photon energy at this level is totally blocked, or basically, if we just remember our physics basics, it should be absorbed somewhere. So it's not reaching AM 1.5. So that is a place, let's say Seattle, for example, at 48 degrees. So in Seattle, you get nothing when the photon energy is here, there, lots of absorption there. And this is sort of expected, right? We thought it will be lower anyway due to dust and other things. UV, ozone layer, is helping us a lot. So what do you think causing these spikes here?
Clouds.
Why here? Yes?
Yeah, because of the clouds, maybe over there.
Because of the cloud. So why only these specific points? If the cloud should cover really all of it will be much smaller, right? If you think it's shading.
Maybe. I know the peak point from 0.3 to 0.6. I know this one.
Okay.
The solar spectrum, which is.
That's good. Okay, so this basically is caused by components in our atmosphere. And these are something we are probably useful. But this gives you something we have talked about last week, and we'll talk about it again, is the global warming effect of CO2. CO2 is absorbing lots of that photon energy in the infrared region, which is basically heat rather than light. So this is probably a good proof for says more CO2 will not trap more heat. But let's get back to our solar radiation. So this is the spectrum. You can see it gets the peak here on the visible region. We get some infrared, ultraviolets, and a bit even from these sides with X and gamma rays and so on. Now the challenge when it comes to solar collectors, when you design your solar collector, you design your semiconductor layers with a specific band gap in them to work with a specific electron volt energy of the electrons. So you can make a solar panel which works like really good with very high efficiency, but on red light only, or green light, or blue, or whatever. The problem is you get the light mixed up. So that will mean your panel could be great in a certain wavelength, but you don't get much of that. And that's why the efficiency of solar panels in a range of 20s for single junction. Now, recent years bring research of having two junctions. How about I have, I think I can do some good sketch, hopefully. Yeah, it's not part of your class. So, what's happening these days? You get basically a junction which can absorb red, let's say. Now these colors are really just examples. It works at 20%, but it's built in a way that it let other wavelengths to pass through. So you can put your second junction under, which absorb green. And then I think the best you can do is at the moment 3 layers. So if you imagine 20% each, then you can get up to 60 looking into 1 square meter. Of course, you don't get 20 from each after putting them on top of each other. 45 is typical for multi-junction nowadays in the market. So this is a solution for the spectrum. If we can find another solution which will make these solar cells work on the wider spectrum, then we can increase the efficiency of solar cells by many folds. Okay. One more line. This is the black body radiation at the temperature of the sun. And you can see it goes really nice over the spectrum. And there where we got the theory of the sun construction and how it emits energy and light. So photovoltaic, which is what we are really after. Typical efficiency about 20. You get it out in the heat with the dust and the soiling effect. You get it much lower. You can do concentrated, but you need cooling. There are many ways to harvest that. This is again a typical figure. So it depends on material, temperature, and of course where you are fixing it. Very important thing if you are going to be in this field. The nameplate is always referring to the standard condition. If it says 200 watts at standard test condition, that is 25C, unless it's mentioned something else, and 1000. Well, the panel, normally you get the label on the panel, so cell temperature, yes.
Cell temperature, it's not ambient temperature. It's
No.
cell temperature. So it's equivalent, I guess, to 15 degrees Celsius ambient temperature.
Well, it really depends, but you need the cell to be that. And this 1000 watt per meter square. So if you get less than that, you get less. Temperature is, especially if we talk about the Gulf region, most of the cases it is more than 25, especially when you have a good solar radiation. Maybe winter, and of course in the night.
What about the air mass?
Air mass is, I'm talking about the nameplate. Some of them will also mention that.
1.5, it's
1.5. But again, when you install it somewhere else, you need to consider the conversion from that. Perfect. Anything on solar energy before we move forward? No? Anybody work in the solar energy field? Yeah? Anything to add? Some tips, tricks? Nothing? Good. That will take us to another resource related to our renewable resources, and later we'll come to fuels, wind energy. Now, wind energy, today I'm going to really touch on it because you have a full lecture on fluid mechanics, and that will cover wind turbines as a basic. If you are a mechanical engineer, you should be really familiar with that. Other engineers must have seen it somewhere. So this is the fluid power, or the wind power in here. Half rho is the density. I think I do have them. Yeah, no. A is the area, and then U, or sometimes V, is the velocity of your wind. So you can see it depends on a cube of, it depends on the rotor diameter, but on a cube of the speed. That means if you get 1 kilowatt per meter square at 6 meters per second, if you double the speed, you will get 8 kilowatts per meter square. And that highlights the effect of wind speed on the generation and the rated wind, which is most important in this case. Now, if we just want to draw that, this one here, with respect to wind speed, we get a curve which looks like that. So, wind starts blowing, and then your energy will increase. It will double, triple, and then your energy will boom up. But any of you have seen a power curve from a wind turbine? Does it look like that?
No.
It doesn't look like that. Why?
Cut
Cut off. So what I should add to make it looks like one? You mean it will stop?
There should be cut in, cut off, right?
Cut in and cut off. Well, this is basically sort of cut in. There is nothing when the speed is low. But then you are mentioning cut off at high speed. How about the shape of it? Yeah.
Constant or a particular speed.
Yes, exactly. This is actual wind turbine power curve. And I just want you to look at the scale here. This is 5 meters per second, and at 10 gets to about 20. 15 stays at 20. If we just go back quickly, you can see at 20 what we are getting based on our like the formula, and then how much we are getting. We are reaching like 4,000 kilowatt. So this doesn't happen in reality for one main reason, which is generator. If you turn it faster, it doesn't matter anymore. It will reach its saturation for generating electricity. So you run it at rated speed, you get what you get. And that's why there is a rated speed at 10 or 12. If you run it faster, it doesn't really matter. Then the wind can blow even much faster. It will reach a dangerous level for your turbine, and you will decide to shut it down. Now the blades themselves, they move. So as the speeds increase little by little, the blades will adjust their direction to reduce the speed and make it to the rated speed. But it will reach a point which cannot, then it will basically cut off in there. Which is sad. You have lots of wind, but you can't just watch it. Again, this is a field which is going on research. Years ago, the blades were not moving. Now we have moving blades, and we have also very intelligent systems to protect these wind turbines, because the investment is very high when you put a wind turbine in any farm. Yeah.
So is there any specific reason that they are in Germany they are putting the wind turbines into the sea?
Well, there are many good reasons for that. First of all, the wind flow. It's going to be open space, so you can imagine the wind speed and flow. You can easily predict it, and it can continuously go.
But is it again going to be more dangerous because of the sea, the high?
Well, here your measures will be coming. So it depends on your data from that specific area. You will decide which type of wind turbine and which sort of technology you put for protection. But what you need with wind is as much continuous wind as possible.
So there is no curve change in the sea over time.
And technically, you calculate the power the same way. In the sea, you have lots of area, so you don't want to worry about land. You get lots of wind, so you don't need to worry about buildings and blocking it. The other thing in land, you can develop the country. So what is now desert or mountains, maybe in 20, 30, 50 years, this will be build-ups area. So where people don't like wind turbines, people don't like many things. But wind turbines, especially in Europe, there is lots of things against them. So in the sea, even in the sea, they still, well, at least they don't see them. Okay? Now the other thing is, which I think the world will be moving to, and hopefully some years' time, is the more of distributed generation. So you will forget about having a planet which covers that country. Everything will be distributed based on where these resources is, and then you can tap to it. If these are, you can imagine, run by private sector, you will pay for electricity. You don't care where this electricity comes from. It could come from a solar farm on North Africa, or it could be coming from a wind turbine in the North Sea. Combined, of course, with solution for the transmission of all this electricity, which is happening. We'll hopefully see some examples of that later today. Okay, so wind turbine rating for a wind speed of 10 meters per second is there. Now, typical efficiency is 50%. When we say about wind turbine, where is this 50% on the graph? Where do you think?
The rated RPM?
At the rated RPM, just when it started. This is the base efficiency. Why? Because as you move there, you are getting more energy, but you are getting the same output. So your efficiency is really dropping as you go that way. So it's really at the rated, and that is the best point to operate. Turbine produce less at all over other times. Now, when we talk wind energy, there is always limits. So PIT's limits in this case is the maximum you can do is 60. If you make an ideal wind turbine, you will get 60 energy harvesting out of it. Similar, you will see in thermodynamics, there is the Carnot cycle. You cannot exceed that. Similar to what we have seen in this graph in here. There is a rated RPM for the generator. It doesn't matter what you do after that. So there is always limits, and these are the things to keep in mind for wind energy. Capacity factor, something you have seen last week. And then that will let us move forward. Water energy or hydropower. Probably I got just a few slides with the statistics. It's rho GHQ. Now always keep in mind, probably Dr. Amber will cover that. Rho here is for the fluid, which is mostly water. The previous one is air. So don't mix things up when you work with these calculations. Typical efficiency here is much higher, 60 to 80, and even, okay. I think I'm talking about this. 80 to 90 is the typical efficiencies because it's direct conversion from mechanical to the shaft of the generator and turn it immediately. Now, if we just talk about renewables in the world and focusing on hydro, this is 100% of the world capacity or output out of renewable resources. And you can see hydro is taking majority of that. We have hydro stations which still on operations since the 40s, 50s, and we do have stations which are nowadays being developed. It's very stable technology and only increasing in size or the scale these days. Now that was in 2010. This is a bit more recent, and you can see the hydropower and ocean sort of stable, moving a bit slowly, but you can see solar in here and wind having really good jump. Solar mainly, wind also is increasing. This is just to give you the feel of how renewables are moving forward. So anything on renewables? No?
Excuse me?
Yes, please.
Regarding the geothermal,
Yeah.
I heard some projects, for example, if you drill and after some depths, and if they heat up the water, you can use it.
Where? In Dubai or UAE or
No, in
certain
general.
places?
Yeah.
Well, see, if you want to harvest or work with geothermal, because it can work both ways. For example, if we are talking Dubai and UAE, if you just get to the water level, water is normally at fixed temperature. So you can use it to dissipate heat and use a heat pump to cool things. But if you want heat and lots of heat, that is something you cannot do anywhere. There are certain places like Iceland, for example. They've got very hot waters nearby, so you don't need to drill very far. And then you can put your coils or circulate your waters from there, and you can generate the steam to drive your turbines. Because this much heat you need is not about heating your domestic water. Otherwise, it's not going to be economical to drill that deep just to get 50 liter, 100 liter of hot water heat. So it's really location specific. There are certain countries which are making lots of use of that, but then other countries, they don't have it, which again, this brings us to the distributed generation part, where you can have generation from different sources and different places. Okay. So this will bring us then to slides related to fuel, including fossil fuels as well. I think I will cover a few of them, then we'll have a short break, then we'll finish up with the rest. So let's start with some global figures. This is oil production and consumption. Now, from now onwards, we are going to talk more of fuels. And fuels will cover oil, biomass, coal, and we'll just have probably one slide on uranium as well. So this one is just to show you where the production and where the consumption is taking place. Production, lots of production in the Middle East, then less is being consumed in the Middle East compared to all these other areas. The legend of the graphs and the colors are at the top there. So you can see that although the Middle East is consuming a little bit only, but you can see there's a clear increase, while some earlier developed area sort of fixed. Like if you took Europe, North America, sort of fixed. It's huge compared to that, but sort of fixed moving from the 70s until 2010 in this case, in this graph. In order to sort of link the numbers together when it comes to reserve, production, and so on, specifically about fossil fuels, there is a basic model which is presented in the textbook, and you should be able to check it in there. It is Hubbard's model of reserve. Here I'm going just to cover some of the basics and show you how does it look. Then you can check it out. I have to mention there are some statistical equations mentioned that we don't really use them a lot. So they are mainly for your information. You should be familiar with the model, the shape of it, and how does it work. But if you need to plug numbers in it, you can always refer to the textbook. So you don't need to remember these equations. Okay, so here are some definitions. Ultimate recoverable resource is Q infinity in this. This is the maximum you can recover from any well or any mine. It depends on what you are getting, or any rig. Cumulative production is how much of the resources we have used by now. So what we have get last year together with this year, and then this will always rise up. Then the difference between them is the remaining. So you started with something. This is what you have, and until now we use this much. Here is the balance. So basically, you say there are this million barrels available of oil in certain place. We have used 500,000. How much balance? Now what we are interested in is really to see how the reserve look like after doing these calculations, and then look into the production rate. And the production rate will basically decide when you will finish that. And we will come next and we'll say the oil will finish in this many years, the gas will finish in this many years, and so on. If you divide them, you will get the time scale, like how many years left of each resource. Here is how the model looks like, and it's basically two graphs. So here, I'll start from 0 in the middle. I'll tell you why in a second, but I'll tell you what it is. So here is, let's say, 200, 300 years ago. You don't know there is such resources available. By the time you get to know there is a resource. Then you start to access that resource. Then production gets faster and faster because you master how to get that resource out. Until it reaches a time where it's getting a bit harder to get that resource, or it's more expensive. Like you need to dig deeper, for example. You need to transport further. You need to use chemicals. You need to use a specific equipment. So that will immediately affect your production rate and will slow it down. And this will keep slowing until it reaches a time where everything is exhausted and that source or data storage is over. Yeah? The zero is in the middle here because we call this the peak. So if we are talking oil, this is the peak oil. Here where you have consumed, let's say, the easy one. Everything next is going to get harder and slower. So you should be able really to explain that. You should be able to draw it if you want to explain the model. Okay? Any issues on the blue one? Yeah?
Yes, please. Again, so the blue one represents what?
Represent your production rate. Production rate. How much you are producing of anything. So you start with nothing. You don't produce it at all. You don't know it's there. Then as you know how to use it, you master using it or getting it out, you produce more and more until it starts to get expensive or harder to produce. And then that will get you low until you finish up everything.
Okay. Where are we now exactly
And when?
in this model?
And oil and gas and UAE in the world, that's a big question.
In the world.
In the world, well, we will see some scenarios. There is worst case scenario, which says like very limited numbers of years left. But we will see next a very good example of this peak, which is the coal in the UK. Because the coal in the UK started, reached the peak, now is finished. Oil we are still producing, hopefully we'll keep producing for a good while. But yeah, it's difficult to tell where we are. But something which is very interesting to mention here, sometimes if you are just reaching the peak and things start to come down, then actually that is not the actual peak. Things will get up much higher, and then another peak is the actual peak. An example for that is gas. Gas in certain places reach these peaks, but then after a few years, shale gas came up, and then that has now a new big peak. So what you need to look is really the last one, and you need to see the complete picture before you judge on it. Cumulative production is the blue one. This is basically how much you have totally produced.
Black one.
Yes. So what happens here? I'll start again. You don't produce anything. You start production, and you can see they go together because you are just starting with production. So this is adding up, adding up, adding up. Then when this starts to increase, you see they diverge, and this gets higher and higher. So this area under this curve is the maximum you produced at all given time from that specific place. This curve represents how much you are producing at any given time. This is cumulative. You add everything together. You get that point? Anybody have issues?
What is the x-axis exactly? Is it the rate of production?
This is the production rate, yes.
So once it hits the peak,
Yeah.
it resembles that we are extracting more and more as we progress towards the positive x-axis.
It means here it's getting harder or more expensive to produce.
X-axis. Is it telling us we are going
This
to
is time, basically. This is time.
So, regarding the shale gas peak, so the production rate has two peaks. So, what about the cumulative production rate? So it can
Will increase.
will increase.
Will keep increasing. Like I will give you example. If we just have 2 buckets and we are filling it with oil, well, small bucket. So 1 bucket is what you produced in 1 hour. If you want to check onto how many you produce in 2 hours, you will add the 2 buckets together. But that still means you produce 1 per hour. So here you will add everything together. Here only what you are producing at any given point of time.
So,
Basically, this market will tell us when we're going to run out of this resources.
This is basically a statistical model. Sometimes you can use it to estimate, but it's more to represent a specific case of production. But you can use it as a model of production and reserve, mainly. Okay, if you check textbooks, I think 1 or 2, and chapter 2, you will get more information about that. Okay. So this is the fossil resources in the UK. This is UK oil and gas. And you can see here is a reserve actually showing in orange. But I think the next one represents more of what we was talking about. Oh, what is that? 1 second. No, we'll check it out later. It's coming next. So some notes here to keep. Reserves is not what's there, because there is no point if you know there is something there, but you cannot access it. Is it too far, too complicated, too expensive to access it? You cannot consider that as reserve. Reserve is what you basically can bring it and can sell it in today's market. So you can use it as a commodity.
Excuse me?
Yeah.
Just add one thing, because most of the cases, whenever companies or investors, so when they say there are two types of reserves. One is, for example, for oil, there is initial oil in place,
Yeah.
which represents like 100%
Yeah.
oil, which is estimated, and then there is recoverable.
Yeah.
So, of course, it's not equal. Recoverable it means like almost 1/3 of the
Yes.
initial oil in place. So, just and also proven reserves, there are like a couple of A, B, C plus.
Yeah, we are not going to go in that details, but it's really important to know that the oil in place or whatever that resource in place is not what you can get. But the good news, if it's in place, maybe in 10 years, 20 years time, you will have the technology to access it. So it's always a good news, even if you don't be able to access it, is not. And this is what you was talking about, original oil in place. So about 35% of it harvested, roughly. 20% is quoted as average rate. So this all will get then the investment really, which is on the demand supply. You know, when oil is more expensive, exploration can be funded because it's worth. When the oil is getting down, some companies will forget about the hard oil and gas. They will get to the easy one. So here's to answer your question. How many years left? How many years do you think left for oil, gas, and coal? Let's start with oil. The worst case scenario. So these figures which you will see next here are the worst case scenario. It's like from the darkest sources out there. What do you think for oil, worst case?
80 years.
In years. 80 there, anybody? Sorry?
50.
50, what else? I feel like I'm in auction running it. Anybody else?
400 years.
I think it can believe more like 200 or 300 years, because there are even some resources.
Well, that is probably because you come from a place which is oil rich.
Well, most probably there are places that wasn't.
Yes,
discovered.
it depends on the usage, it depends where, but again, we are talking about the worst as a worst case scenario. So,
Doctor, I think it's more important to look at the demand rather than how much is
business
that.
as usual. We are assuming business as usual. We'll use on the current rate because we know, based on what we see last week, we are only going to increase in our energy demand.
No, I mean, we might have another source of energy which is more feasible.
True, but for the worst case scenario, we are assuming business as usual.
35.
Let's talk about gas and coal, then we'll move forward, we'll show you the numbers. So do you think gas will be more or less than oil? More? Okay. Coal? Less. Let's see the numbers then. So these are the worst case scenario. Yeah? I think you can start storing oil by now. Gas 50 years, coal 90 years. Now all these, it depends on basically what we have seen in the previous slides, the accessible resources, and business as usual is very important. Now if we want to look why coal is 90, why everybody thought is less, let's see how much is there out in the world. So here is the coal in orange or yellow maybe. Oil is red, and then brown is natural gas. So you can see there is lots of coal in many places, not in the Middle East, but we got lots of oil. Yeah? Oil is cleaner, easier to transport and to store, so we don't mind. Then gas, you can see, is in lower sort of quantities to oil. You can see much lower gas. Gas here was over, so shale gas came in, and then on top, yeah.
I think South America has more oil than the Middle East.
Well, not in statistics.
No.
Not compared to what's happening in the Gulf region, not to say big Middle East. No.
I think they recently discovered, like maybe 5 years ago.
So
I need to cover this
back
one, that's why
back
they
to
are
that
here.
question. Oil reserves and how much they
If they have more oil,
This is
they will stay
fuel
there.
reserves.
You can check all these figures, but then this is what we got. So we have seen the worst case scenario in here. Now I'm not saying this is an exam question, but I'm not saying it's not exam. It's previous exam question actually. When, for example, in the last part, the non-numerical part, a question will say, what are the expectations for the fuels, how much we have. So getting familiar with some of these figures, even if it's a worst case scenario, is good. If it's not a worst case, another scenario, if you know more about it, it will be always good. So moving forward, now we have seen all these. Now, oil. So this is the current reserve estimate by British Petroleum in 2011, estimated about 54 years. And then again, there is a possible extra reserve from the new accessible reserve. CO2 equivalent is just to give the feel of if we used all that, how much we are going to emit. Similar thing here into gas. So this is natural gas reserve around the globe. What's missing from this? Anything missing? Shale gas. So you can see how the picture looks before and after the shale gas. So this brings us to last week when we mentioned when we manage to access a new resource, it might fully change the picture, the prices, and even how attractive research in specific areas are. Okay. Now this, which I was looking for it actually, is the UK coal production. So here you can see, in the Industrial Revolution, when everything started, we had coal only. And then, actually coal is what derived the Industrial Revolution. We managed to access coal and start converting it to useful energy. So production in the UK increased and increased and increased, and early 1910 or 1912, it reached a peak. And you can see there are a couple of spikes in here, like it's almost finished, then you manage to access another, or find another way, or find another mine to get, and then start to struggle, getting less and less and more expensive, and then now it's dead. So this is a typical example of the peak. So this is peak coal of the UK.
Doctor, those troughs, aren't they because of World War II?
This is also a possibility in there, yeah. But this is, see, is not, yeah, the one was here, 18, right? This is about 21. So yeah, there is a drop there, and then 45, not much affected really. But what we are interested in is the peak in 1910 and 12. So this is a typical peak. And then you can see here, imports start rising. As what you have is over, you will need to import. And here where all the problems start. Because you need to secure these import sources, you need to secure the prices and so on. A bit more on coal. So here the top 5 coal producing nations, China, United States, India, Australia, Indonesia, and the rest of the world is there. You can see China is increasing probably 2 to 3 folds. US is pretty stable, together with, there is a bit of an increase in India and Australia. Okay, a bit more into a coal picture, and that doesn't include shisha coal, as mentioned in there. So China is almost approaching 50% at 45, and then again the other 4 nations we saw, rest of the world. That will bring us really to fuels now, and fuels are a store of energy, and normally as a chemical energy. So we got here long list which we are familiar with. Nuclear energy in here. Uranium is mostly used, but then there is also research on thorium and also other ways. What's good about fuel, they release energy only when needed. So we can store them, transport them, leave them in a place until we need them. And normally you get heat out of them from combustion. And you will be talking a lot about combustion and calculating CO2 emissions, and we will see next where all these emissions come from. So also we'll try to list some of these examples in here. We'll talk about coal, biomass, and maybe hydrocarbons as well, which is gas and oil. Biomass, it's really wide range. Wood, ash, and so straw, and many things. We'll see examples in them. They represent about 10 to 20% of the world's energy. We have used them for thousands of years for cooking, heating, and also for other uses. Nowadays, they are being increasingly used as alternative resource, especially if we talk about renewable biomass. And we'll also talk a bit on its emissions. The tricky part here, it comes in broad range of chemical compositions, more complex than just hydrocarbons or coal in the case of carbons. They come also with some humidity levels. They come dirty sometimes, which you'll need to deal with the dirt, and so on. Now, looking into the chemistry for them, this is the general term, but in our course, we are going to consider all biomass to be CH2O. So you don't need to worry about other types of biomass. When we talk combustion, CO2 is a must. So it's always O2, CO2, then we can get H2O if there is H in the first place. So this again will be covered in combustion in more details, where you will need to calculate and balance all these equations, calculate CO2 emissions and our energy content. Well, why we have this one here to get you started first and to think if the biofuel or the biomass fuel is renewable and carbon friendly. What do you think? Is it?
Yes,
I think it's renewable, yes, but carbon free, no.
it is carbon free.
Why not? Because it produces CO2?
This is one of the reasons.
No, but the plant which is used, it will also consume CO2.
Yeah, but then you are using the area.
Yes.
But we are
So
also-
it's basically here, these plants, if we just take a simple wood as a biomass, it's basically a store of solar energy from photosynthesis, and it uses CO2 in there. So CO2, you add water, and you add energy, which is solar energy, you get a tree. You chop it down, you go camping on the weekends, and enjoy the desert. So, but this is not the full picture. Looking into these, you can say, yes, it's probably net zero carbon. What comes in comes out, but we know there is always efficiency and losses. Not all the wood you grow here is going to burn there. There's losses in the production, losses in transportation, losses even during the burning. So it will normally, it's certainly friendly, but it's not zero, because you are sort of cycling. And also this part, nowadays, it's not simply just go plant the tree, forget about them, and come after 50 years, you have trees ready to work in your, let's say, biomass burning station. It's not that easy. You will need to have transportation, which emits CO2. You need to take care of all these farming processes, which emit CO2. And this all will be taken in consideration when you do your CO2 emissions calculations. So typical questions will tell you, we get this much wood, 20% is regrown, 10% is lost, do your CO2 emissions or savings. So this is biomass here in this case, and this is just a quick example on how they vary in their energy content. Energy, we normally going to refer in multiple of these fuels as megajoule per kg. Like a kg of oil or wood, how many megajoules will give you. So you can see like freshly cut wood, 11, because it's wet. You dried it, air dry, you get 16. Oven dry, you spend energy on it, but you get it to 20. If you convert it to charcoal for your shisha, is 29. So again, you will need to spend certain time or energy to get better quality of the same fuel. That will take us to coal. It's still relatively cheap. We have seen there's lots around the world, and it's the most available one compared to oil and gas. But it's dirty. It's very dirty to transport, to mine, to deal with it, and to deal with its emissions. It's complex. It depends where is that coming from, millions of years of pressure and heat, what sort of composition it is in, and so on. What we care about is the carbon. So always when we talk coal, you will be given a carbon content. How much of that coal is carbon? And it's not 100%. 70%, 60%, 80%, and that is what's going to be useful, a fuel for you. A typical equation looks like that, C plus O2, CO2. Nowadays, when they say clean coal, you basically do capture and storage of this CO2. And then that will mean it's a clean coal. But the clean coal coming in is still as dirty as hell. Anything that cannot burn will stay as ash. You need to deal with it in different ways. Here I got also some examples for you. The wood part is really for reference, but the most famous ones are lignite and anthracite in there, and you can see 30 megajoule, and we got 20 compared to wood at 20. Fixed carbon, which is the carbon content, is here. and then you get also moisture, ash, and so on. This will be useful to calculate your waste later. So if you burn 1 ton of anthracite, you will get 150 kg of ash, and so on. So that will bring us to what's left on the list of fuels?
Nuclear? Nuclear?
Nuclear, right after the next one.
Hydrocarbon.
Hydrocarbons. So hydrocarbons will apply into our petroleum products and gas. They are hydrocarbons because basically you have a carbon and then hydrogen attached to it. This is the most simple one, CH4, which is a gas, which we refer methane normally. And then as they increase in numbers, they get their names. Butane, and then this is, for example, octane with 8 of C. If you look closely to these pictures, what do you see? How is the number of hydrogen relates to the number of carbon? It's always double, plus 2, one at the start, one at the end. So this is something you will find it in the textbook. You need to keep it in mind. Always the number of H is double plus 2. Yes. Yes, exactly. I don't have it in the slides, but yes, CnH2n plus 2. It's there in the book. Will be covered in more details with Dr. Amber. I removed them from these slides just to make this a bit going faster on fuels and avoid repeating them again in combustion. Now, if we want to look into the reaction equation in this case, this is natural gas, assuming is methane, CH4. These figures are coming from the balanced equation. This is the energy content. And this will be provided for you for each different hydrocarbon based. One thing I don't know if you noticed so far with all the equations we have seen, we are including only O2. But in reality, combustion happens with air, not with O2. So nitrogen gets involved in there, and might take certain parts. We'll see which one is really going to be covered more for you. One more thing here probably to mention is the natural gas sometimes is a mixture of gases. When natural gas comes, it doesn't come as CH4. It's not that easy. It might have at least 2 gases plus CO2, for example. When you have CO2 coming in, that CO2, the same CO2 will go out. Of course, we are assuming very basic combustions, because for you guys, whoever is coming from probably chemical engineering or mechanical engineering with combustion focus, you know that combustion is not as straightforward as that. Especially if nitrogen comes in the combustion chamber, then all these start to de-associate. So you'll have NO, NOx, CO, CO2, and the list goes really long. Whatever comes in will burn with O2 and with your fuel and get complicated, but lucky for you, we are not covering any of that. It's going to stay at this level only. You will need to do some mass balance, and then you will use that into your calculations. Now that will bring us to, okay, here's another example of octane, cetene, and so on. They are all really following the exact same theme. Now here we'll talk more about nuclear fuels for a couple of slides. When it comes to uranium, or nuclear fuels, because there is research now on thorium as well, or maybe platinum and so on, the price is really depends on how much is there. The quality of basically the ore you get. The quality will will vary the price, and will vary how much CO2 emissions you are putting into mining and transportation and the processing until you get the fuel ready for a nuclear plant. So this is very important to consider. Nuclear power is emission-free in generating heat from the station itself. But for the fuel, that's called life cycle, getting it from the mine to the station, use it and deal with the waste later is which will add lots of CO2 emissions. Of course, won't compare to C, and especially if you make a good big cycle. If you use all electric vehicles and the transportation, but then you power them to the electricity generated from nuclear plants, you are cutting your transportation emissions. But then you are getting emissions into building the batteries and these cars and so on. So it's really the life cycle which you need to consider when we talk about emissions. But certainly in operation is clean. Some people think it's dangerous, maybe not. I don't know. What's your thoughts? Are you with or against nuclear? Why?
Energy, but the problem is the nuclear waste.
Yeah. So if
The
we
nuclear waste is the problem.
so if we find better ways to deal with this waste, you find it
Radioactive elements. Radioactive elements.
within the station or within the waste, you mean?
Even in the waste.
Yeah.
And during the process.
Mm-hmm. True, but then many people are scared from the radiation within the planet if something happens like what happened in Japan or other
Actually,
places.
yes, as per the last research, and we did that programs, if you compare like nuclear, solar, wind, and whatsoever, you will find that you will go for the production rate for like how much per kilowatt hour. So nuclear is the lowest for the production rate, as the money to produce 1 kilowatt hour from electricity.
You mean cheaper?
Cheaper, yes. So the second thing, as per the new research for the nuclear safety, so the safety about the emissions and how to get rid of all these emissions, and the nuclear safety inside the power plant itself also very enhanced. So you can see, like if you want to sign an O&M contract for a solar park or for a wind farm and for a nuclear power station for like 1 kilowatt, you can see like for nuclear $130. If you go for solar park, it will cost you $200. So for sure for like a couple of years, from 3 to 5 years. So if you go to nuclear as a capital cost or as a running cost, it's much cheaper. And also it's very durable.
Yes, but then
Solar, you have to get out from all the solar parks that are 20 to 25 years. Wind farm can also stay more than 20 years.
perfect.
But nuclear power station, you can see in France, it's starting from 1950 or maybe even like older than
Nuclear?
No, sorry, the cool resource.
Yeah.
But nuclear
You have them probably from the late 60s, early
yeah, from
70s.
60s, and you can go to US.
Yeah.
You can find a lot of nuclear power plants and still achieve.
Yes, but this is only one part of the story, because if you compare this with coal electricity is one of the most expensive now.
Yes.
But we have seen statistics is still one of the major components in it. So it's not that easy to get a nuclear planet with all the, first of all, the political parts of it, then getting to convince people to get a nuclear planet next door. This is another challenge. And then secure your fuel, that is one. And of course, waste. But we are moving, I think, in a good direction. I mean, 40, 50 years ago, we used to dump the waste in the sea. Now, at least, there is longer term arrangement. The only problem is, there is no guarantees on this longer range storage. I mean, you can do computer modeling for 1,000 years, 10,000 years. But how really that stable that storage, when you say is going to stay there for 100,000 years? Nobody can guarantee that. one big earthquake, unexpected, could change all this plan.
But recently, one British company, they successfully did nuclear fusion.
Yes.
Yes.
And they said like within 10 years they would be able to produce it commercially.
Well, hopefully. Because see, it all again depends on the market, the demand, and who's going to fund this research, who's going to build these plants. The other thing is commissioning and decommissioning. I actually just before the class I removed one slide, probably I'll show it to you. I used it last year. But let's look here before we move forward. So estimates is estimating 90 years on uranium, so it's not even much better than the others we saw. So it doesn't solve the problem. It generates lots of power, maybe emission free on the station, but if you can't sustain it more than 90 years, then what happens after that? Emissions will really depend on what you are getting. $80K, 130, I think 260 on here, third one, and then that is the price which is moving on these years. Now here's some more information on nuclear fuels. So uranium has several naturally occurring radioactive isotopes. Now this will hopefully, I think the next one will show us the heat content. Remember when we saw oil or gas or coal, we was in the range of 20 to 50 megajoules per kg. Now you can imagine what we can get from that. So much smaller amount of fuel get us way more power than it is. That's why it was attractive back in the day when all these started to be built. Now, of course, if you work up further with that, you can enhance it better. Now, this is the enriched uranium in this case. Of course, new technologies are coming up every day. So let me just get that slide up. I think it's here. Continue recording this one. So this was exactly 1 year from now. I used it in last lecture. It was, this lecture last year. This was a station in America. It was the oldest operating a nuclear power plant at that day. It was due to close Monday. My class was also on Sunday, so it was the next day. Now this showing you how much it contributes to New Jersey's electricity here over all these years. So nowadays is not much. It's closed already, over a year now. But why I brought it back in today, just to cover the point mentioned there about the decommissioning. So how long do you think decommissioning of this will take? It stopped operating last year. How long do you think it will take to decommission it, to delete it, to get the land back, and then you can make a new development, if it's a station or something else?
I think it's more than 50 years.
Yeah, anybody else?
So during from starting of operation till the end of the...
No, just decommissioning, since you close the doors until you have it empty land.
Maybe 8 to 10 years.
8 to 10 years.
Even more than that.
Yeah, so actually it was nearby, it's about 60 years. So some of the structure actually will stay there until 2075. This is something you consider when you develop a station, when you will use this area again to do anything else. So that all goes into your cost, initial cost. You need to buy this land, keep it for that, and then do a very slow decommissioning process at the end. Okay. So here we got some statistics from the US for 2017, and this here, fuel used in the US. And you can see petroleum and gas taking majority. they still use coal. Nuclear is a very big portion compared to any other country. Not everybody can afford to have this big piece of nuclear in there, but Americans can. So this is a mix. And of course, renewables are rising up. If you break down the renewables, you will get also biomass getting a good amount over the last years. So 19, almost 20%, and then biofuel, another 20. This is all biofuels. Wind, 21, only a little bit of solar. So this is just to give you a picture comparing all these resources and the fuels we covered today. This is more of the world energy. And again, considering the source of this energy, coal, oil, and natural gas taking big share. Biofuel, almost as we used to. And then a bit of nuclear and a bit of hydro electricity on top there. Here we got energy used by fuel again. Now this is of the world and per capita. So biofuels. Now you can see biofuels is reducing in here, but you can see is the same or a bit increasing in there. Why it's reducing by capita? Because less people now have access to electricity and, let's say, modern fuel sources compared to biomass. Everybody had only biomass option 100 or 200 years ago. Then that is reducing. There are some people nowadays that still use only biomass for heating and cooking and so on, but that is reducing. But looking into the energy of the world consumption, biofuels are increasing, and a good example of where this increase comes from is here, how this biofuel, biomass waste and wood is contributing to the energy. So all these actually work like a puzzle pieces. You put them together and get you a better understanding of what's happening in the world. Probably I have one or two more. This is the UK, 1980 to 2011. This is by sector here. So you got transport in red, services there, industry, and then domestic. We have seen similar ones from Dubai last week. You can always refer to them. And then this is the last one, again from the UK, which is how the resources was used during the last 40 years. I don't know how clear is that, but this is oil, yellow is electricity, gas in here, renewables and other. This is the dark, but this dark, the small dark on top of there, and then solid fuel in here. These are resources used until 2008, 2010. Anything, guys, you want to add? Anybody have any point relevant to what we have?